Hello, so today we're going to be looking at the interview problem string compression. And this is an algorithm data structure string question, and it can be found in page 91 of the book Cracking the Code Interview. So this is the problem right here. It says implement a method to perform basic string compression using the counts of repeated characters. So for example, the string AAB CCCCC AAA would become A2 B1 C5 A3, and this is because we have two A's at the beginning, so A2. We have one B following that, so B1. We have five C's following that, so C5, and we have three A's at the end, so A3. So what we can then do is then expand this string out by writing out the number of characters using the numbers next to them, and we can get the original string back. And this is compressed because this string takes far fewer characters than this one. It also says there's another condition here. If the compressed string would not become smaller than the original string, your method should return the original string. So if this ends up being longer than this original string, this is clearly the shorter or more compressed string, so we're supposed to return this one. It also says you can assume that the string only has uppercase and lowercase letters. That's another one right here. So let's think about a brute force solution for this. So for me, the brute force solution would be that we would look through each of the string. We would keep track of whatever character it is. Once the character changes, we put the character and the count that we had into the new string. So let me just summarize this. So iterate through string. String keeping count of current character. By this I mean if we were looking through the string, we would see A. We would keep track of the number of A's that we encounter. When character changes, add old character and its count to new compressed string. And finally, check, or actually we can say here is compare length of original and compressed string. And what we want to do is return the shorter one. So I'll do a quick trace of this one. So if we had string s equals a, and then b, c, 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 and a at the end. This should actually just be two A's at the start. So what we do is we'd have a compressed string C. So we'd go through the string. So this is our scan pointer. So currently we're at A, and so we're at A, move to the next character. So we've encountered two A's so far. And the next character is B. So what we do is we do A2 into the string right here. We move to the next character, B, and then the next character is something different. So we write B here, and then we write 1. Then we move to the next character, which is C, and we encountered 1, 2, 3, 4, 5. So So we're up to 5 now. The next character is different, so we write in C and then 5, and then we're back to A again, but this is a new A because it's not a repeating set. And we have 1, 2, 3. And we continue this until we reach the end of the string, at which point we'll write down the last character as well. So this will be A3. So this is our compressed string right here. So if we were to think about the order of complexity for this, iterate through the string would be order S, where S is the length of the string, because we have to go through each character. Now, this is the bit right here that causes difficulty, because this add the old character and its count to new compressed string. This bit right here, that's a terrible line. This is actually k squared, and k in this case is the length of the two strings combined. And the reason for this is because string concatenation, how it works is it takes the original string and the new string, and then it creates a new string, putting all those characters together. So we have to read the original string, read the new string, create an array, and then join a string together. And this takes k squared, which is the length of the combined strings. So this process takes this long, and k is the number of unique sequences. So here would be 1, 2, 3. Whoops, is it 3, 4? So this will be 4 squared, for example. This length comparison, string lengths are instant, I guess. This is order 1. So our this is not time. This is not space. This is time. Time would be order S plus k squared. K is number of I guess consecutive character sequences. And if we look at space complexity for this one, so the only extra space that we're doing is we're doing this. So this is going to be at order S. We could say we use extra space for concatenation, but it won't be larger than order S. So space is order S, where S is the length of the string. Now we've achieved the optimum. Well, we haven't achieved the optimum, but we've achieved a pretty good space complexity. But the problem is the time complexity here has a squared in, which is generally not good. So we can improve upon this, but this is a good brute force solution, so we can capture that for now. And if we think about how we would optimize this, we can see that the bottleneck right here is this string concatenation here. So the main way that we can avoid doing this is instead of creating strings, joining them together, then splitting them, joining, splitting them, joining, we could just keep a character array, which we can add items to, because array insertion is constant time. And at the end, we can join that array into a string. So that's how we're going to be doing this. So I'm going to show you how this works. So again, we have our input string. So this is A. So let's say we have S, which is our input string, which is A. I'm going to give myself a bit more room here. So we have S, which equals A, B, C, 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 A. And I'm just going to write down the indexes of this, so the character indexes. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the length is 11. So the length of the string is 11. And we're also going to have our character array. So I'm just going to call this C for compressed. We're going to have 2 pointers. So we're going to have scan pointer, which is here, and we're going to have an insertion pointer, which they both start at index 0. So here's how it works. So what we're going to be doing is we're going to be we're going to have a variable to keep track of the count. So that's the count of each character that we encounter. So first things first, so we have count starts at 0. We look at the character, we scan the character, and we increase the count by 1. What we do here is we check if the next character is different, which it's not. So we can skip ahead and we can just move on to the next character. Now we look at A again and we increase the count by 1. So A now has a count of 2. Then we look at the next character and we can see that it's different. So we do this check to check if either the next character is different or if we're at the end of the string like before. And then what we do is we check that wherever our insertion pointer is, we check that insertion pointer +1 is less than the length of the string. And the reason we do that is because remember our compressed string at maximum can only be the length of the string right here. If not, we need to return the original string. So what we want to do is we want to make sure that we don't insert more characters than we're allowed here. So we check if insertion +1, which is index 1, is less than the length, which it is, so it's fine. And then what we do is we write in the character of the scan pointer, which is A, and we write in the count here, which is 2. We move the insertion pointer along by 2, so the insertion pointer is now here, and we reset count back to 0. Once again, we move the scan pointer is at B, so we increase the count by 1. We check and the next character is different. We check if the insertion pointer +1, which is index 3, is within this allowed range, and it is, so it's fine. So we write in B here, and in insertion +1, we insert the count here, and then we move insertion along by 2. We reset the count, and we move scan along. Now we're at C, we scan, we increase the count. Next character is the same, so we move the scan pointer, increase the count. We do this again, we do this again, and we do this again. So now our count is at 5. Now the next character is different. So what we check is insertion +1, which is index 5, within this allowed range? It is. So what we do is we write in C here, and then we put in 5 at insertion +1. We move insertion along by 2. We reset the count. We move scan to the next index. And now what we're going to do is we're going to restart our count. So A at 1. The next character is the same, so move it along. The next character is the same, so move it along. And now we reach the end of the string, so we can't go any further. So we either check if the next character is different or if we reach the end of the string. So now that we're at the end of the string, we check if insertion +1, which is 7, is within the allowed range of 0 to 10. It is. So what we can do is we can insert A here, and we can write in the count at insertion +1, which is 3. So now that we reach the end of the string, we simply can check if C is shorter than S, and in this case it is, so we can return C. And when we return it, we want to return it as a string rather than an array, so we just join this together, and we get to return A2, B1, C5, A3, which is our compressed string right here. And the benefit of this is that we can see that we didn't do any concatenation, we're just adding to an array, and we've only had one pass through the entire string. So if we think about how this would look in terms of code, so the return type is going to be a string, and the name of the function is going to be called string compression, I guess. So if I write string compression, it takes in a string S. So that's this string right here. So the first thing we want to do is we want to set up our character array. So what we're going to do is say character array C equals new character array. And we want it to be of length s, because remember, if it's longer than s, there's no point doing the compression. So we only need to do s.length as our length of the new array. We want to have our count variable, so this is going to be an int count, and we're going to set this equal to 0. We're going to have our insertion pointer, so we're going to have ints. We're going to set this to 0. We're going to have our scan pointer, which is also an integer. Remember, these so-called pointers are just indexes, so scan, and we're going to set this also to 0. Did we have anything else? No. Okay, cool. So what we want to do is we want to iterate through all the characters of the string. So the way we can do that is, because we're going to be incrementing the scan pointer, we can just say while scan is less than s.length. So what this means is it will continue until as long as scan is less than the length of the string. In this case, it goes up to index 10. So the first thing we want to do, like I said, is we would increase the count when we scan the character. So we'd say count equals count plus 1. And the next thing we do is we do our check. So the check is A, have we reached the end of the string? Or B, is the next character different? So what we want to do here is say if s, so this is scan pointer. I'm going to just rename this to s because it's just easier. So if s, no, I can't actually, sorry. This is s is the string. I was getting confused there. So if s at the scan pointer is not equal to s at scan, running out of room here, scan plus 1, or scan is equal to s.length minus 1. So in this case, we're checking if is the next character different to whatever is at our scan pointer, or is scan at s.length minus 1. So if scan was at index 10, we would need to stop there as well. So what we need to do next is we want to first check if we have enough space left to insert. So what we want to do here is we want to say if insertion plus 1, remember, because we need 2 characters here. So whatever insertion is, we need to check if the character next to it as well, because we need to write in the number is, let's say, greater than or equal to s.length. So for example, if insertion was here and insertion plus 1 was here, we know that the compressed string is going to come out longer. So what we want to do in this case is we simply want to return s, because remember, we're supposed to return the original string if the compressed one is going to end up being longer. Otherwise, what we want to do is we want to say c, which is our compressed string, at insertion is equal to s at scan. So for example, when s was at index 1 here, and insertion was a 0, we would scan whatever is at s, which is this, and we'd write it into the insertion. And what we also want to do is we want to say c at insertion plus 1. So this is the character next to it. So this will be, if insertion was 0, this would be this 1 right here. And we want to set this equal to whatever our count was. So we want to set this equal to count. And then what we also want to do is we want to reset count to 0. So count equals 0. And in each iteration of the while loop, we want to make sure that we move scan along. So scan equals scan plus 1. And once we reach the end of our string, we get to the very end. We know that if our compressed string ended up being longer, we would have returned the original string. So that's fine. So what we can do now is we know that the compressed string is actually shorter. So we can just return c.join, and we're going to just join it with an empty character. So it just joins all these characters together. So that's our optimized algorithm. So let's have a look at a time and space complexity. So initializing an empty array is constant time. This bit right here, while scan is less than s.length, this is order s, where s is the length of the string because we're going through each of the characters in the string. Performing this check, it's comparing two characters. It's not comparing two strings. So comparing two characters will just be constant order. And accessing a particular character at the string like this is also constant, so it's fine. This should really be s dot character at I rather than character at scan rather than s dot scan, but whatever. Yeah, comparing numbers is also order 1, so that's fine. Yeah, this check is order 1 as well. And then these array insertions are also order 1 because inserting into an array for a given index is constant time. And joining the string right here would be order c, which is whatever the length of the compressed string is. But if we think about this, c will always be shorter than order s. So we know that this, for a fact, won't be larger than order s. So our time complexity would be order s. We're going to ignore the constants, plus order s, a maximum of order s, which is still order s. If we think about the space complexity, so this right here will take up to order s characters, because remember we create an array with s dot length, so this is order s. And that's pretty much all the space that we end up using. So our space complexity is order s. So we've achieved the optimum time complexity here. This is the best that we can expect because we'd have to scan through the string at least once. In terms of space complexity, it might be possible to do it. Actually, it's not. So this is also the optimal space complexity. And the reason for that is to build a compressed string, you would need memory for that. It's impossible to do it without using additional space. One thing we could do is do some kind of check if the length of the compressed string would be shorter, and in that case start overwriting the original string. But it doesn't really say that we can modify the string. We could. I'm not really sure, but we definitely would need to do the length check in that case, because otherwise we're supposed to return the original string, and if we modify that, we can't return it. So I guess I would say that this is the optimal solution. So this is our final solution. So yeah, let's think about, take a better picture of that, capture everything. So now what we can do is we can think about starting to code this out. So I'm going to be using TypeScript again. So this method is called string compression, and it takes in a string s and it returns a string. So the first thing we're going to do is set up our character array right here. So let's make this a little bit bigger. Yeah, sorry about that. So the first thing we're going to do is we're going to initialize our character array. So we can't do character arrays in TypeScript, so this is just going to be a string array. So const, it won't be const, well, it can be array. Const C, and it's going to be a string array equals new, and I guess we can put the length in. I'm not sure if we can put the length in TypeScript, but I can try it. Let me just Google it. Equals new array string s.length. There we go. Had to look that up. Actually, other thing that I've noticed is we're using this s.length in a lot of places. So we can just move this into a number called SL. And this would save us from having to look up the length of the string. It doesn't take long, but it's just one quick optimization we can do. Then we're going to have our count. So count. So count is 0. These have to be lets because we're going to have to modify our insertion pointer. And finally our scan pointer. So let's scan number equals 0. And then we can do our while loop. So while scan is less than SL. So again, remember SL is just the length of the string. We want to firstly increase count by 1. So count equals count plus 1. Then we want to perform our check. So if s.character at scan is not equal to s.character at scan plus 1, or scan is equal to, we could do greater than or equal to be safe. Actually, you know what? We should move this here because if we were to try this when we are at the end, this is going to cause an index out of bounds error. So we should always perform this check first. So then here's what we're going to do. We're going to check if the insertion plus 1 is in the valid range. So if insertion plus 1 is greater than or equal to SL, so this means the index is out of bounds, because at max it can be s.length take away 1. We want to return the original string. Otherwise, what we want to do here is we want to say a C at the insertion pointer equals s.character at scan, and C at insertion plus 1 equals count. We want to reset count to 0. What's wrong here? Oh, this is because it's a number. I guess we could just write this as, so basically the issue is we have a string array and I'm trying to put a number in there, so we can just do a template string like this. And finally, in each iteration, we want to make sure that we move the scan pointer along. So scan equals scan plus 1. Another thing I noticed is we're using this twice. So another thing we could do is move this to a variable, but I'm not going to really bother. It's fine. But yeah, that's another optimization. And finally, we know that this is actually shorter. So what we can do here is we can do return c.join and just join it like this. I'm just going to read this again. This information we haven't really used, so I'm kind of concerned that there's something to do with this that we haven't implemented, but I can't seem to figure it out myself. We can actually change this to SL takeaway 1 because if we reach the end index, the compressed string and the original string would be of equal length, but it says that if it would not become smaller, then we need to return the original. So even if it's the same size, we would need to return the original. So that's our string compression function right there, so that we can just test this out now. So if I copy this, so console.log string compression. If I just put the string in. So let's see what it comes out to. Hopefully it works. Oh. Oh, actually, I forgot one step, which is we need to move the insertion pointer along by 2. So that's also something that I did here, but I forgot to do here. So we want to do insertion equals insertion plus 2. So this would be, I'm going to do this here as well, just so I don't forget it later. So we would need to do insertion equals insertion plus 2. We need to move the insertion pointer along by 2. Sorry about that. So let's try it again. And we can see that we have our compressed string back right here. Now, let's say that we just had 2 A's and 1 B. So here the return string should be, the compressed string would be A2B1, which is actually longer than this. So we should actually return the original string AAB. Yeah, that's correct. If we had AABB, here it would be A2B2, which is still equal to the length of the original string. So we should be returning the original string here again. And we can see that we are. So yeah, it seems to be working. So this is the optimal solution for the string compression problem, at least my solution. Yeah, so, and it achieves this in order S time complexity and order S space complexity, which is pretty good. I assume there is probably something better because we're not really making use of this information. So if you know a better way to do this, leave a comment and I'll be very curious to know what that is. So yeah, thank you for watching.